Well, hello again, Dr. E. We're going to continue our lessons on energy. In our first lesson, we defined energy as the ability to do work, where we're essentially talking about mechanical work, the easiest type of work for us to explain. We said that work is equal to a force times a displacement. In the case of mechanical work, that force was the force of gravity, mass times the gravitational constant, working over a displacement distance d. An example that we gave was lifting a 50 kilogram weight, 2 meters. The work then and the energy required to do this work would be 50 kilograms times the gravitational constant times the 2 meters. In that case, 980 joules. Joules being the measure of energy, which is named after James Prescott Joule. In this lesson, we're going to talk about potential energy and kinetic energy. You can see by our little illustration the different meaning. Potential energy is related to position, kinetic energy, energy in motion. Okay, let's delve into each of these. So potential energy, energy associated with position. So once we have lifted this 50 kilogram weight 2 meters over our head, it now possesses potential energy. How much potential energy? Well, just that mass times the gravitational constant times the distance, mgd. The positional potential energy is just equal to the amount of energy required to lift that weight 2 meters above the ground. 50 kilograms times g, the gravitational constant, 9.8 meters per second, times 2 meters, 980 joules, or almost 1 kilojoules. If this weight were then allowed to fall to the ground, it could transfer its energy to do some other type of work, including lifting another weight above the floor. Well, how might this be done? Well, in this slide, we show an example of a pulley system. Let's say that the first weight on the left, the 50 kilogram weight, is lifted by our weightlifter 2 meters above the ground. And we have a pulley system, and it's connected to a second weight. And let's say that this second weight is 25 kilograms, or half the weight of the first. What would happen if the weightlifter let go of the 50 kilogram weight? What would happen? Well, it's pretty obvious. The 50 kilogram weight would drop and it would elevate the 25 kilogram weight. Or in other words, the potential energy related to the position of the 50 kilogram weight above the floor, that positional potential energy could do work by elevating a second weight. Second weight that weighed less, of course. Okay, that makes sense. That's how the potential energy stored in the first weight when it's lifted above the ground can be used to do work on the second weight. But could all the potential energy of this first weight be transferred to potential energy in a second weight? Sure, we could elevate a smaller weight, but what if the second weight had a mass of 60 kilograms? Think about it. No, you would conclude that if you let go of the 50 kilogram weight on this pulley system, it would not be able to elevate or to lift the 60 kilogram weight because the 60 kilogram weight weighs more. Well, that's pretty obvious, but what if the second weight was exactly 50 kilograms also? Would it reach a balance, or would it? Think about it. As you think about this, you may think of other subtle things like, what about that pulley? Is it a frictionless pulley? And things of this sort. Things that perhaps we'll talk about later. But in general, this is the way that potential energy can be used to perform mechanical work on a second object. Well, what is kinetic energy? Kinetic energy is energy associated with motion. Now, if you've had other courses in science, you've probably been told that kinetic energy is equal to 1/2 mv squared. That's a fairly common equation that people learn. Kinetic energy is 1/2 mass times velocity squared, where v is the velocity of the moving object, and m, of course, is the mass, and half is just a half. So if you were to have a 50 kilogram weight that was lifted to the height of 2 meters, and then you dropped it, all of the potential energy of that elevated mass would be converted to kinetic energy as the weight falls to the ground, or in the case of the left, as the ball rolls down the hill. Okay, that makes sense. Potential energy can be transferred to kinetic energy. Okay, but what would be the velocity of the dropped weight? Let's see if we can calculate that. Since we know the potential energy when the mass is elevated is equal to the mass times gravitational constant times the displacement distance, and we previously calculated that to be 980 joules, we can then equate that potential energy to kinetic energy. That is, PE is equal to KE, so that 980 joules is equal to 1/2 mv squared. And then if we just solve for velocity, do a little math, we would calculate that the final velocity of the weight of the barbell when it falls down would be 6.26 meters per second. It's falling pretty rapidly. But the important thing that you might notice in this problem is that the velocity of the falling object is independent of the mass of the object. Okay, let's look at the math to see how that works out. So if kinetic energy is equal to potential energy, which we can then say 1/2 mv squared is equal to mass times the gravitational constant g times the distance that it's elevated. And if we cancel out the mass from both sides, multiply by 2 to get rid of the half on one side, we have that the velocity squared is equal to 2 times the gravitational constant times the height, or the distance to which it's initially elevated. And taking the square root, we get the velocity is equal to the square root of 2 times g times d. There's no mass in the equation. Now, this may or may not seem surprising, but it was an important discovery by Galileo Galilei. You may recall the oft-told story of how, up until the time of Galileo, based on the teachings of Aristotle, people thought that a heavier object would fall faster than a lighter object. I mean, it was just sort of intuitive. The bigger they are, the harder they fall. Well, yes, the bigger they are, the harder they fall, but not necessarily the faster they fall. Now, of course, things were complicated by air resistance. You could drop a feather and it's very light and it floats on the air currents. But what Galileo did, if you remember the story, he climbed the Leaning Tower of Pisa, Italy, and had two objects of about the same shape so that they would have about the same air resistance. And he dropped them, and they landed at essentially the same time, thus experimentally showing that the heavier object and the lighter object, when they have about the same air resistance, would fall with the same final velocity, which was independent of the mass of the object. Okay. The links at the bottom of this slide are to a couple of YouTube videos of reenactments of Galileo Galilei's experiment. We might watch those if we have a chance. Okay, then the question is, if potential energy was converted to kinetic energy, where did the energy go after the object lands on the ground? Well, it is converted to another form of kinetic energy, which is heat or thermal energy. And it may become transmitted to vibrations of molecules in the floor or the air. An interesting example of this was is bungee jumping. You've probably seen YouTube videos of someone bungee jumping off of a tall building. And of course, the bungee cord or spring the person will oscillate up and down. And actually, this is an example in which potential energy is converted to kinetic energy, but at some point, the person stops bouncing up and down on the bungee cord. And at that point, the initial potential energy has been dissipated as thermal energy or as perhaps screams by the person doing the bungee jumping. All right, now on to power. So Scotty, James, we need more power. Power is defined as work done per time. Work done per time. So we can lift a 50 kilogram weight to a height of 2 meters. This requires a certain amount of work. But this work can be done over a short period of time or over a long period of time. And the work that is performed over the shorter period of time corresponds to the larger input of power. Now, I want to show you two videos of a weightlifter, and just watch for a second and see which one has the most power. Okay, you get the picture? Dang, the one on the left is lifting the bar much more rapidly than the weightlifter on the right. So the one on the left is exhibiting a much larger power than the one on the right, even though they're both lifting the same weight to the same height, because the one on the left is lifting it more frequently. Power is measured in watts. And this is after James Watt, another scientist and inventor, who enhanced the steam engine. Oftentimes people say James Watt was the inventor of the steam engine. Actually, the steam engine existed before James Watt, but he made very significant enhancements or improvements to the steam engine, made it much more efficient. 1 watt of power is defined as a joule of work per second of time, joule per second. That is, 1 watt is 1 joule per second, and therefore 1,000 watts is a kilowatt. And you've probably heard of a kilowatt because we measure electrical power in kilowatts. So let's quickly review by focusing on some units that we use. For force, we measure force in newtons, after, of course, Sir Isaac Newton. And a newton is a kilogram meter per second squared. We measure energy in joules, named after James Prescott Joule. And a joule is a newton meter in terms of mechanical type of work. And power is measured in watts, where a watt is a joule per second. So that you can see that these units of measure are somewhat interrelated. Force, energy, power. Force in newtons, energy in joules, power in watts. Okay, we will pause again, have a short quiz, and when we come back next, we're going to talk about thermal energy, leading us to then talk about the first law of thermodynamics. All right, we'll catch you next time. Be careful not to drop your barbell.